Now, having discussed the thermodynamic stability of the nucleus and how you can take changes in mass and convert them into changes in energy using Einstein's equation E equals mc squared, let's go ahead and talk about energy changes for nuclear reactions. Here we're going to discuss nuclear fission reactions. In a nuclear fission reaction, you're going to take a heavy nucleus and break it up into smaller nuclei. In this example, what we're going to do is take uranium-235 and perform a fission reaction on it by bombarding it with a neutron. When you bombard uranium-235 with a neutron, this nucleus can absorb the neutron, forming the isotope of uranium, U-236. Now, this is a very unstable isotope of uranium, and so this is going to fall apart and break up into smaller pieces. There are many different decay reactions that are possible, but just one of them is that uranium-236 can break up and disintegrate into barium-141 and krypton-92, and then importantly, this reaction also results in the release of 3 neutrons. This is what we would refer to as a chain reaction, because you use a neutron to start the reaction, and the reaction generates neutrons, right? So when these neutrons get generated in the products, they can go back through the reaction and they can cause more uranium-235s to react. As a result, this could cause the reaction to become self-sustaining. This brings us to the concept of what's known as critical mass. So having a critical mass means that you have just a high enough concentration of uranium-235 such that you're able to sustain the reaction on its own. Meaning that when you perform this reaction, right, you produce those 3 reactions. And when you have a critical mass of uranium-235, one of those 3 neutrons is capable of finding another uranium-235 nucleus, allowing the reaction to propagate. The other 2 neutrons escape. And so that gives you just enough uranium-235 that you're able to allow the reaction to propagate on its own without you having to add more neutrons in. If you were to have a subcritical mass of uranium-235, that would mean that there's not a high enough concentration of U-235 to sustain the reaction. When there's a subcritical mass, you're going to have a situation where, on average, less than 1 neutron will find another uranium-235 nucleus. And so eventually, the reaction will just kind of fizzle out unless you add more neutrons in. You could also have a situation where you have what's known as a supercritical mass. And this is when you have such a high concentration of uranium-235 that the reaction not only is self-sustaining, but it will start to go out of control. So when you have a very high concentration of uranium-235, remember that the fission reaction results in the production of 3 neutrons. So maybe on average, more than one of those 3 neutrons will go on to react with another uranium-235. And so that's going to cause this sort of avalanche process where the reaction just starts to happen so fast and it kind of begins to exponentially increase in its rate. We can visualize this in a video where we're going to have a whole bunch of mouse traps. And you can imagine every single mouse trap is like a uranium-235 nucleus. And every mouse trap will be spring-loaded with a ping pong ball. So think of the ping pong ball as being a neutron. We're going to drop a neutron or a ping pong ball into this array of mouse traps, and you're going to see what happens when you have a supercritical situation where the reaction goes out of control. All right, now here we see our mouse trap that has a ping pong ball loaded in it. So again, think of this as being a uranium-235 nucleus, and think of that ping pong ball as being the neutron that will escape when a fission reaction occurs. We're going to go ahead now and drop a neutron in to activate the reaction. And when it happens, a neutron gets ejected. So now let's take a look at an array of uranium-235 nuclei, or an array of mouse traps. A ping pong ball, remember that represents a neutron, is going to get dropped in, and then we're going to see the chain reaction that will occur. All right, so you saw that happen really fast and out of control. So this is going to be a slow motion version that will allow you to visualize the process of the chain reaction occurring, where one reaction results in the release of a ping pong ball, then that's going to cause another ping pong ball to get ejected, and then another ping pong ball, and it starts to go out of control. It's like an avalanche process, because on average, one ping pong ball is able to find more than one other mouse trap. It starts to happen very fast and very out of control like that. I think it's nice to kind of have a visual like this here, to imagine what's going on at the nuclear level when you perform a fission reaction like that. All right, now let's talk about how you would calculate the delta E for this reaction. In this example, we're asked to calculate the energy that will be released if you were to react 1 gram of uranium-235 according to this fission reaction. Now, in order to solve this problem, you have to be given the masses of all of the species that are part of this reaction. So here we're given the mass of the uranium-235 nucleus, the barium-141 nucleus, and the krypton-92 nucleus, as well as the mass of a free neutron. And we're going to use these to first calculate what the change in mass is over the course of the reaction. And so to find the delta M, we're going to have to do the mass of all of the products minus the masses of all of the reactants. All right, now let's go ahead and do that. The change in mass will be the masses of all of our products. Here we have a barium-141 nucleus, so that will be 140.914 grams per mole. And we're also going to have a krypton-92, so that is 91.926 grams per mole. And we also have 3 neutrons, so we'll do 3 times 1.675 times 10 to the minus 24 grams. And we want the units to be compatible, right? So we have to convert the grams into grams per mole, right? This is the mass of 1 neutron. So to find the mass of a mole of neutrons, you'd need to use Avogadro's number. So you're going to have to say that 1 mole is 6.02 times 10 to the 23, right? And I've divided by the 1 mole here so that I get units of grams per mole, like how everything else is grams per mole. Now from that, I'm going to subtract the masses of all of the reactants. So minus and then a big bracket that all the reactants go into. For the reactants, I have a uranium-235, so that's 235.044 grams per mole. And I also have 1 neutron that's been added, so that's 1 times the mass of our neutron, 1.675 times 10 to the minus 24 grams. And then remember, right, we have to also put this into grams per mole, so multiply by Avogadro's number again to make it grams per mole. All right, I'm going to go ahead and calculate what the change in mass is over the course of the reaction, but I have to move things up a little bit. So I'm going to move to another slide and just shift things up a bit here. All right, what we find is that over the course of the reaction, the mass defect, or the change in mass, is negative 0.184 grams per mole. This is a pretty substantial change in mass, right? If you were to react 1 mole of uranium-235, you would see that the mass would have decreased by 0.184 grams. That's a pretty substantial amount of missing mass. And again, that has to be accounted for, right? The law of conservation of mass says that you can't just, say, oh, well, I guess it's gone, goodbye, right? That mass must have been converted into energy. And to see how much energy it was converted into, we're now going to use Einstein's equation, E equals mc squared. I kind of like being able to use that equation, right? I feel like I'm really smart when I use E equals mc squared. So let's go ahead and do that to convert the change in mass into a change in energy. We saw previously that you can express it as delta E equals delta mc squared. And remember that any constants can be pulled in front of the delta. So delta E is equal to c squared times the mass defect, delta M. Therefore, the delta E for this reaction will be the speed of light squared, so that's 3 times 10 to the 8th meters per second squared, times our mass defect of negative 0.184 grams per mole. And then don't forget that the mass has to be in kilograms per mole, right? Because energy is going to be in units of joules. Joules are kilograms meters squared per second squared. So don't forget to do that. Don't forget to divide by 1,000. All right. So now what we have for our units are kilograms meters squared per second squared. So that's joules, and then per mole. Therefore, the delta E for our reaction that we calculate will be in units of joules per mole. And the value that you're going to get is enormous. It is negative 1.7 times 10 to the 13 joules per mole. That is a tremendous amount of energy. Now, that's how much energy would be released if you were to react a mole of uranium-235. The question is asking us how much energy is released if you use 1 gram of uranium-235. We'll start by converting the 1.0 grams of uranium-235 into a number of moles. All right, we have 1.0 grams of uranium-235. And then to convert to moles, we're given the molar mass, right? That was given all the way back at the beginning of the problem. We were told that it was 235.044 grams per mole. And it's very important that you put all of those decimal places in here. You want to carry all those decimal places throughout the entire problem. because, right, even all the way out to like the thousandth or the 10,000th place, it's going to make a difference, right? These small changes in mass result in enormous changes in energy because you're taking them and multiplying them by the speed of light squared, right? So this is one of those rare times where you do have to carry all the decimal places through your calculation. What you end up finding is that this comes out to 0.00426 moles of uranium-235. Now, the last thing that you need to do is take the number of moles of uranium-235 and multiply it by the delta E to find what amount of energy is being released. All right, we have 0.00426 moles of uranium times the delta E, which was negative 1.7 times 10 to the 13th joules per mole. That allows us to cancel out the units of moles and find what amount of energy is being released when you react 1 gram of uranium-235. And it comes out to negative 7.1 times 10 to the 10th joules. So you release 7.1 times 10 to the 10th joules of energy for every gram of uranium-235 that reacts. That is, again, a tremendous amount of energy. Just for the sake of comparison, the amount of energy that is used in the form of electricity throughout the entire state of California in one day is 2.6 times 10 to the 15th joules. So if you were to react just 100 moles of uranium-235, you would be able to generate enough electricity to power the entire state of California for a day. It really is remarkable how much energy can be released by a reaction like this. Now, is this the only reaction that can happen? Does uranium-235 have to split into barium-141 and krypton-92? Well, no, that's not the only possible fission products. There are many other reactions possible, and here are just a couple of them. You can also split uranium-235 into tellurium-135 and zirconium-100, or there's also a possible set of fission products where you make cesium-137 and rubidium-95, and there are several others. In fact, all of these reactions are happening simultaneously in a fission reaction for uranium-235. So it's not like the only possible products of barium-141 and krypton-92, and that's not the only reaction that is happening. I will say that for exam questions, you'll be told what the reaction is, and you'll be told what all the masses of the products and reactants are so that you can calculate the value of delta E for the reaction. You know, that will be specified to you, and you will not be expected to predict the products of fission reactions, just because there are so many different products that are possible, and it's just not predictable. Now, as I mentioned before, the amount of energy that is produced by this reaction is enormous, and it's for this reason that people consider using nuclear energy as a source of power. And so in nuclear power plants, they do reactions like this, where they perform fission of uranium-235. This is a schematic of a nuclear reactor, and here we're going to have a core that is generally going to consist of a critical mass of uranium-235. So that critical mass allows the reaction to be self-sustaining, but in a controlled manner, right? We're not going to do supercritical and have it go out of control like all the ping pong balls. It's going to go in a controlled manner where, on average, for every reaction that occurs, one neutron finds another uranium-235. Now, the energy that gets released from this reaction will heat up water until the water boils. And when the water boils, then the steam that gets generated comes out and it will turn some turbines. And that converts into mechanical energy, and that's going to allow you to produce power. Now, the core is also attached to some control rods that can be put in to capture any excess neutrons so that you're able to sustain a critical mass with a controlled reaction. So if the reaction does start to go out of control, you can move the control rods in so that you can capture the excess neutrons and just slow the reaction down before you end up having like a really bad situation, like let's say a nuclear meltdown. And I think it's kind of interesting to see the applications of what you're learning about here and to see how nuclear reactions are done in power plants to generate electricity. And I think that it's really nice to see how the information that you learn in Chem 1C can be applied in the world around you. All right, up next, we're going to talk about nuclear fusion.